this lesson, we're going to be learning about graphing absolute value functions. Absolute value functions are functions in the form f of x is equal to the absolute value of x. And remember, f of x just tells us that we're talking about a function. It's the same as saying y equals the absolute value of x. So first, let's refresh ourselves on what absolute value means. Absolute value is a number's distance from 0. So if we're talking about the absolute value of 3, we're talking about how far is the number 3 from 0 on a number line. And because we're talking about distance, it needs to be a positive value. So the absolute value of 3 is 3. If we look at the absolute value of negative 3 is also 3 spaces from 0. So the absolute value of 3 and the absolute value of negative 3 are both 3. The absolute value of negative 8 would be positive 8. The absolute value of 3/5 would be 3/5. And the absolute value of 0, well, that would be 0 because it's 0 spaces. Now, if there's a negative out in front of the absolute value sign, if we say the absolute, then that means negative 1 times the absolute value of 3. The absolute value of 3 is 3. So negative 1 times the absolute value of 3 would be negative 3. So let's go ahead and get into the graphing part. In order to graph these, what we've done is I've created tables for us, and I've chosen some x values, just some easy ones to work with, negative, positive, and 0. And so what we're going to do is going to plug these numbers in to our function. So if x is negative 2, that means we're talking about the absolute value of negative 2, which would be positive 2. The absolute value of negative 1 is 1. The absolute value of 0 is 0. The absolute value of positive 1 is 1. And the absolute value of positive 2 is 2. So I'm going to plug these in, our values that we got. And we're going to graph them as ordered pairs. The ordered pair negative 2, 2. So negative 2, 2 would be right here. Negative 1, 1. 0, 0. 1, 1. And 2, 2. So you'll notice that this graph, the graph of an absolute value function, makes this V shape. And this is what we call the parent function. All of the graphs of absolute values will look something like this parent function right here. You'll notice it has a vertex at 0, 0. Half of it is decreasing, that's this part to the left, and this half of it is increasing. Then when we talk about these, we also talk about their domain and their range. Domain is all of the x values that are graphed. And so we're talking about the numbers here along the x-axis. Every one of these numbers gets used. Like if x is 3, y is 3. If x is negative 4, y is 4. Every one of those numbers gets used. So the domain is all real numbers. But for the range, when we look at the y's, you'll notice that this graph only exists up in the top 2 quadrants. So none of these negative values get used. So the range, when we're talking about the y values, is y has got to be greater than or equal to 0. So our domain is all reals. That's because x can be any number. But for this graph, y has to be greater than 0. Because no matter what we put into that function right there, our result was going to be a positive value. So like I said, this right here is the parent function for all absolute value functions. So what we're going to do now is we're going to look at some equations that change that parent function up a little bit. So here we're going to graph the f of x equals the absolute value of x minus 2. So you can kind of see the parent function in there, and then you see that we've included a minus 2. So I've chosen the same values for x this time. And we're going to plug those in. The absolute value of negative 2, and then we're going to subtract 2. Well, the absolute value of negative 2 is 2, minus 2 is 0. Then we're going to plug in the negative 1. So that gives us 1 minus 2. This is going to give us 0 minus 2, so negative 2. 1 minus 2, negative 1. 2 minus 2 gives us 0. So here's our ordered pairs here. Negative 2, 0. So negative 2, 0. Negative 1, negative 1. 0, negative 2. 1, negative 1. And 2, 0. We have our function right here. And it's going to continue on in both directions. So for this one, all of the x's again are going to get used. So you're going to notice that our domain is all real numbers. This capital R with an extra vertical line is just the symbol for real numbers. You're welcome to write it out. And the range, this time we did have a couple of negative values that got used, but only down here to negative 2. So you'll see that nothing really goes beneath this line. So all of our y's are greater than or equal to negative 2. Now if we want to compare this graph to the parent function, let's see, the parent function would be right here. That's the one we just graphed. So you'll notice that this one is the same shape, but it looks like it's been shifted down 2. That's what that minus 2 did to it. It shifted it down 2. We call that a vertical translation. Okay, let's look at some more. Here we have f of x equals the absolute value of x minus 2. This time our 2, you'll notice, is inside the absolute value sign. So we'll have to subtract the 2 before we take the absolute value. So we're going to do the absolute value of negative 2 minus 2. So that's the absolute value of negative 4, which would be 4. The absolute value of negative 1 minus 2, so that's negative 3 inside. So the absolute value of negative 3 is 3. Absolute value of 0 minus 2 is going to be 2. Oops, is that right? Let's see. 1 minus 2, that gives us a negative 1, which would give us an absolute value of 1. And 2 minus 2 is 0, which gives us an absolute value of 0. 4, 3, 2, 1, 0. And so let's go ahead and plot some of those points. Now this one looks like we're only getting a line instead of a V. So maybe we should try a few more numbers. What happens if we plug in 3? That gives us the absolute value of 3 minus 2, which is 1. So we notice that must be the point right there where it starts turning back up. Like I said, absolute value will always be a V. So if you're getting a straight line, you may need to plug in some more points. We can continue this. It's going to continue at that same rate. So this time, if we compare it to the parent function is right here. We kind of want to have that one memorized so that we can easily compare. We notice that the shapes are the same, but this one has been shifted to the right too. We call that a horizontal translation. So this minus 2 in here caused us to have a horizontal translation to the right. So notice that when our minus 2 was on the outside, it shifted us down. When our minus 2 was on the inside, it shifted us to the right. Now, hopefully when you look at that, I'm going to switch back and forth a couple times here. This minus 2, it makes sense that a minus 2 would move us down. But this minus 2, you might think should move it to the left, but it actually moves us to the right. And we'll talk about why that happens here in just a minute. But you want to kind of notice that right now. So let's talk about the domain and range. The domain, all the x values get used. So that's, again, all real numbers. And for the range, it looks like we're only up in the top 2 quadrants again. There aren't any negative y values, so y is greater than or equal to 0. In this video, we've covered the basic parent function, and we've covered what happens when you have something added or subtracted to the function on the outside and on the inside. In the next video, we'll get into a few more different types of translations.